Okay, so this is problem number 19 of the first homework assignment, and the problem states that you have two charges, one equal to negative q sub naught, the other equal to negative 3 times q sub naught, that is a distance L apart, and I've labeled that L sub naught. And so what you need to do is you need to place a third charge somewhere so that neither one of those original charges will move. Now, because they're negative, there's a repulsive force between them, and so normally they would push away from each other. So to counteract that, you need to put a positive charge somewhere in the middle of them. I've labeled that charge q sub 1, and the distance from the left original charge to q sub 1 I've labeled x, and the distance from q sub 1 to the right charge is L sub naught minus x. Now, the first thing you need to do to solve this problem is you need to figure out what x is, or L sub naught minus x is, to figure out how you're going to, or what distance you're going to place the charge. Okay, and you're going to use Coulomb's law to do this. So there's Coulomb's law over on the right, and then you set up the Coulomb's law equation for the q sub naught and q sub 1, and negative 3 q sub naught and q sub 1. And so it's k times q sub naught times q sub 1 over x squared is equal to k times 3 q sub naught times q sub 1 all over L minus x squared. And then you can do some canceling out to get rid of q sub naught, q sub 1, and k, so that all you're left with is L and x terms. And then you can it's just a little bit of algebra to move the squared throughout the L minus x, and then you move around the terms after that and combine like terms, that fun stuff, and it should give you 2x squared plus 2lx minus L squared is equal to 0. And then you use the quadratic equation, which is on the right, and plug in the a, b, and c into the appropriate places in the quadratic equation, and it'll look something like this, and that's going to be equal to x. And then simplify what's under the square root, or do it however you want to, and I simplified in the square root, and then I brought it down. And then at this stage you can get rid of the negative, the minus part of the plus or minus in the quadratic equation, because if you were to subtract, you would end up with an overall negative thing, and it's physically impossible to end up with a negative length for something. Length has to be positive, and so you can just keep simplifying down, and you'll end up with 0.366 L is equal to x. So that will mean the charge is 0.366 times L, whatever L is, away from the q sub naught charge. Now, the second part of the problem is goes pretty fast, actually, and so all you have to do, excuse me while I fold the paper, and so this is the second part of solving the equation, where you're solving for the strength of the third charge. And so it actually is only a kind of two-step process. First you set up the Coulomb's law equation and so the left side of this is the strength of the strength of the repulsive force between the two original charges, and so that's k times q sub naught times 3 q sub naught all over L squared, and that's going to be equal to k times q sub naught times q sub 1 all over 0.366 L all squared, so that way the attraction in this equation will counteract the repulsion from this equation. And so again, you just do some canceling. One of the q sub naughts goes away, the k goes away, the L squared will go away. Make sure to square the 0.366 though. And it will leave you with 0.402 q sub naught is equal to q sub 1. And so the answer to the problem is you need to place a positive charge equal to 0.402 q sub naught, 0.366 L away from the negative q sub naught charge to keep both of the original charges stationary.